Using RSA for asymmetric encryption is a multi-step process starting with the generation of a private key, the creation of a corresponding related public key, the release of the public key then to be used by communication peers for the encryption of data into a ciphertext, which can then only be decrypted by making use of the private key. If the private key is properly safeguarded by an owner, this allows to provide confidentiality to data sent to this owner, even if the public key is public knowledge available to anyone. As opposed to the textbook example of RSA, real-world RSA systems add randomness to the data before encryption to properly provide security to the resulting ciphertext. This randomness is, for example, added via the Optimal Asymmetric Encryption Padding Scheme (OAEP), which uses cryptographic hash functions to randomize the message before encryption. The following demonstration will show how I made use of RSA randomized with the OAEP padding and how I verified that indeed only a small message roughly of the size of the public-private key pair can be encrypted with it. Using RSA requires to first create a public-private RSA key pair, where the public key can then be used for the encryption of a plaintext into a ciphertext, and the private key can be used for the decryption of the ciphertext back into a plaintext. Nowadays, it's recommended to use RSA keys of size at least 2048 bits, and the public exponent E is often set to 2 to the power of 16 minus 1, which is 65,537. It's interesting to once look into a private RSA key containing two prime numbers, each of half the size as the overall key size indicated, which is why I printed the prime numbers to the console. The public key is actually just the exponent we set during the construction and the product of the two prime numbers contained in the private key. I nevertheless thought it would be interesting to see, which is why I also printed the public key to the console. With this public key, I then proceeded to encrypt the name of the scores, for which I required to indicate that I wanted the OAEP padding scheme to work with the SHA-2 256 hash function. The ciphertext clearly doesn't resemble the plaintext, and with this I proceeded to decrypt this ciphertext and made sure to verify that this recovered plaintext really is the original plaintext that I started with. This, of course, succeeded. Next on the list to demonstrate was the fact that with RSA, only plaintexts smaller than the key size involved can be encrypted. The real question is, how much smaller does this plaintext need to be? Answer is that the answer depends on the padding scheme used, and with OAEP, the answer is provided in section 7.1.1 of RFC 3447, which indicates that OAEP allows for messages smaller or equal to the key size minus twice the size of the hash function minus 2 bytes, which in our case is 256 minus 64 minus 2, which is 190. This concluded the demonstration of how to use RSA and how to discover its limitations.